So the first thing that we're going to talk about is what we learned in the Desmos activity, and that is the p-test. So if we have an integral of 1 over x to the p, its convergence or divergence is based on a couple things. First of all, it's based on the bounds, and second of all, it's based on the value of p. So because that's true, what we learned is that if we're taking the integral from 1 to infinity, what happens if we have 1 over x to some power that's bigger than 1 is that this area all the way over here actually converges to some number. Whereas if that p-value is less than 1, it does not converge to some number. It will actually go off to infinity. It never actually gets low enough to where the value ever reaches some sort of limit. Conversely, going the other direction, it's the exact opposite. So if we're taking this area, that converges, the integral from 0 to 1 converges if p is small, so somewhere between 0 and 1, and it diverges if p is big. And so what ends up happening is, just like you saw in the Desmos activity yesterday, this black area gets larger and does not converge if our p-value is bigger than 1, and the red value gets larger and does not converge if the p-value is less than 1, and vice versa. If p is equal to 1, everything diverges, and that's because when we take the integral of 1 over x, we get the natural log of x, and that ends up not working out either with a 0 in there or an infinity in there. Or a 1 in it, like basically it never works out. So that is something that we learned yesterday, hopefully in our activity. Really quickly, we will take a look at what happens with the function 1 over x and then the function 1 over x to the p. So notice as you have 1 over x to the p and p gets larger, everything after 1, the area under the curve between that and the x-axis would definitely be smaller than 1 over x. And the area between 0 and 1 would be greater than 1 over x. And likewise, if p is smaller than 1, then the area after 1 is bigger than the red curve, which is 1 over x. And the area between 0 and 1 is definitely a lot smaller, between the x-axis and the blue curve versus the x-axis and the red curve. 1, 2, 3. I have written on the board what happens when we take both sides of the integral of 1 over x dx. Notice that the natural log of x, when we have the natural log of 0, that's infinity, so that's basically what happens in this one right here. And then in the second one down here, if we have the natural log of infinity, that goes off to infinity. And infinity minus 0 is infinity. So basically, both cases where p equals 1, we get divergent integrals. We do not get an area that actually goes to a number. But that is that cutoff point, essentially, where p equals 1. That's the cutoff point where we have convergence or divergence in either way. And ultimately, that's our first comparison test. So when we were back at the Desmos thing that I just showed you a minute ago, our first comparison test is what happens when we compare things to 1 over x. So now what we're going to start doing is comparing things to other things that we know. So now we know pretty much everything dealing with 1 over x to the p. And so now we're going to start comparing things to that that we may not be able to integrate very easily. So let's take a look at this chart. So if we have f is less than g everywhere in the chart, I will make f in red, and I will make g in green. So notice A has to be bigger than 1, and F is less than G um, everywhere to the right of A. So let's make A there. So at some point, G has to become bigger than F everywhere to the right of A. So if you look at A, F is smaller than G everywhere to the right of A on our picture. So if we know that G of X converges, so we know that G of X converges, that means that this area underneath G from A to infinity goes to some number. So that goes to some number. What does that mean about F? Well, if the green area goes to some number, and the red area is smaller than that, the red area must also go to some number. So in this case, f of x must converge. Now we have the exact same situation, but we know that the green area does not converge. The green area diverges. What does that mean about f? That means absolutely nothing. F could diverge, but f could converge also because it's smaller than something that diverges. We're not actually getting any information. So it could converge or it could diverge, but we don't know. Now, let's take a look at the third situation, where if f is still smaller than g and f is known to diverge. So I thought I moved you. If f is known to diverge, so that means that this red area from a to infinity does not reach a value, then the green area, the area under g, must also not reach a value. So that must also diverge. And the reason for that is if f is too big, essentially, and keeps increasing in value as we go off to infinity, and g is bigger than that, it can't possibly go to a specific number. And that's the direct comparison test. So let's move this out of the way a little bit. Oh, that bounced. So if we move this out of the way, let f and g be continuous functions on a to infinity, and f is always smaller than or equal to g. So as long as we're bigger than or equal to a. We know that f of x converges if we know that g of x converges. Likewise, we know that g of x diverges, the integral, if the integral of f of x diverges. And the exact same thing works if we have the integral from 0 to a or something. If we have the smaller one diverging, then the bigger one has to diverge. If the bigger one converges, then the smaller one must converge. If the bigger one diverges, that doesn't tell us anything about the smaller one. And if the smaller one converges, that doesn't tell us anything about the bigger one. Also, we have what's called the limit comparison test. So the limit comparison test is if f and g are positive functions on a to infinity, and if the limit of both functions as x goes to infinity goes to some value L, where L is actually a number between 0 and infinity, then both of these functions, oops, that box wasn't big enough, both of these functions either converge or they both diverge. We know that both of them do the same thing. So where this really helps is if we have a function with an unknown convergence or divergence value, and then another function with a known convergence or divergence value. If we get L, some number as an actual limit, then we can make a conclusion about the one we don't know. But if we don't get some value, the limit comparison test gives us no conclusion. So we only get a conclusion in the limit comparison test if we get a value for this limit, which means you have to choose wisely on which function that you want to compare it to, basically. We will now do the direct comparison test and or limit comparison test to show convergence or divergence of some of these improper integrals. One thing that's important to note is that you only have to do one on a test or quiz, or potentially on the AP test. You don't have to do both of them, but in some of the problems we'll end up showing both just to show that it works in both, or sometimes we'll show that sometimes it's easier to do one rather than the other. On the first problem, we'll use the direct comparison test. And so we need to directly compare 1 over e to the x squared with something else. And so the first thing I'm going to notice is that e to the x squared is always greater than or equal to e to the x, as long as x is greater than or equal to 1. And since that's the case in our problem, since x is always greater than or equal to 1, I can use this fact. Because of that, I can then divide both sides by e to the x and divide both sides by e to the x squared. And so I have this fact that 1 over e to the x is always greater than or equal to 1 over e to the x squared. Because that's true, if I can show that this function converges, then the other function will converge when I take the integral from 1 to infinity. So I can show that this function converges. So I do an improper integral, I follow through on the steps, and I show that that converges to 1 over e as you take the integral from 1 to infinity of e over 1 over e to the x dx. Therefore, it converges. So by the direct comparison test, I can say, since the integral of 1 from 1 to infinity of dx over e to the x, I don't know why I put dx twice, converges by the direct comparison test, then the integral from 1 to infinity of 1 over e to the x squared dx converges. So that's something that's true. I'm going to erase it, so pause or whatever if you need to go back. I also could have done the direct comparison test by showing that e to the x squared is always greater than or equal to x squared when x is greater than or equal to 1. And since I know that the integral from 1 to infinity of 1 over x squared, then that then goes to say that 1 over x squared is greater than or equal to 1 over e to the x squared for all x is greater than or equal to 1. And by the way, I'm allowed to do that by dividing, and it's not changing the sign because all of these numbers are positive all the time. So since those numbers are positive, I can divide, and it's not going to change the sign. So this is also true, and therefore, since this converges by the p-test, then the direct comparison test says that the integral from 1 to infinity of 1 over e to the x squared dx also converges. So I could have used the direct comparison test in a couple of different ways. Okay, that's number 1. Number 2. What I will probably want to do in number 2 is I will want to show that since I know for a fact that the sine squared x is between 0 and 1 inclusive, I can then divide all parties involved by x squared, which is always positive. And since x squared is always positive, I know that I don't have to change signs or anything. And so I have this situation where sine squared of x over x squared must always be less than or equal to 1 over x squared. Since I know that the integral from 1 to infinity of 1 over x squared dx converges, and sine squared of x over x squared is always smaller than that, by the direct comparison test, and the integral from 1 to infinity of sine squared of x over x squared dx converges. So that is another thing that is true. So we've just used the direct comparison test a couple of times. In problem 3, the integral from 2 to infinity of 1 over root x squared minus 4 dx. Note that x squared minus 4 is always less than or equal to x squared. And that's true for any number, but especially for x is greater than or equal to 2. And that's what we care about in this particular problem. Now note that there's actually 2 issues here, so we would have to do multiple limits in this problem. We would have to break this up where we have the integral from a to 4, where we're doing the limit as a approaches 2 from the right, because you can't actually plug in 2. And then you would have to do plus the integral from 4 to b with the limit as b goes to infinity. So there's actually multiple things going on in this problem with improper integration. But let's just kind of take this at face value right now. Now I can square root both sides because there's no issue with domain here. So since that's the case, root x squared minus 4 is greater than or equal to x for everything in this domain. And then I can divide through, so 1 over x is less than or equal to 1 over root x squared minus 4. And since all these numbers are positive, I don't really have to worry about anything in terms of changing the sign. Since this diverges by the p-test, and it is smaller than something else, that means that that something else must diverge. So, by the direct comparison test, I know that the integral from 1 to infinity of 1 over root x squared minus 4 dx diverges. So that's true. I'm going to erase this, and then we're going to talk about a different case. So if I change this problem to be root x squared plus 4, so if I change that to be this situation, exact same problem, except I have a plus sign. X squared plus 4 is always greater than or equal to x squared for all values of x, but especially x is greater than or equal to 2, which is what we care about in this problem. So when I take a square root of both sides, x squared plus 4 is greater than or equal to x. And then I divide through and I get 1 over x is greater than or equal to 1 over root x squared plus 4. This diverges, but it's also greater than or equal to what we care about. So in this particular problem, I cannot use the direct comparison test because I would get something that's divergent, but it's also greater than what we're caring about. So that would give me an inconclusive result if I use the direct comparison test in this case. So I might have to try something different, like the limit comparison test. So if I did the limit comparison test in this particular problem, and you don't have to necessarily write this down because we'll do more limit comparisons in a minute, but I have 1 over root x squared plus 4. I'll treat that as my f of x, and then g of x, I will make 1 over x. So I want to do the limit of this function as x approaches infinity, because I'm trying to see if this will end up giving me something that converges or diverges. So I can rewrite this just by the laws of fractions to say the limit as x approaches infinity of x over root x squared plus 4. Now I'll use L'Hopital's rule because this would be infinity over infinity. So I can use L'Hopital's rule. So I can say the limit as x approaches infinity is 1 divided by 1/2 x squared plus 4 to the negative 1/2 times 2x. So I would end up with, rewriting this by the rules of fractions, I would have 2 root x squared plus 4 over 2x. That cancels the 2's off, and I end up with root x squared plus 4 over x, which is basically the exact in the reciprocal case of this. So it seems like I'm just going to end up keep bouncing back and forth between these two things. And this appears that it will also be inconclusive. So this particular case, I get an inconclusive thing for both the limit comparison test and the direct comparison test. So that might be a good idea on your own to see if that one converges or diverges. Just kind of explore it a little bit. Problem 4. So we have root x minus 1 over x cubed, and that's the integral from 1 to infinity. So in this case, the first thing I'll do is try the direct comparison test. And so I have root x minus 1 over x cubed is less than root x over x cubed for all x is greater than or equal to 1. That just seems like it makes some sense because the denominator should be the same and the numerator, the one on the right, would be strictly greater than. So since that is the case, let's rewrite the one on the right as a p-test. So I have root x minus 1 over x cubed is greater than or equal to 1 over x to the 5 halves. I know that because root x is x to the 1 half, and I can just use the laws of exponents to write it as x to the 5 halves. This converges by the p-test, and since that converges and it's larger than root x minus 1 over x cubed, that means that by the direct comparison test, the integral from 1 to infinity of root x minus 1 over x cubed dx also converges. So if something larger than it in all spots converges, that means that that one also must converge. Okay, let's take a look at the next problem. So we have 1 over x minus e to the negative x. I'll use another direct comparison test here. I know that x minus 1 over e to the x, which is the same thing as e to the negative x, that must be less than or equal to x for all values of x greater than or equal to 3. So I can say that by dividing both sides, 1 over x is less than or equal to 1 over x minus 1 over e to the x. Since everything is positive, I'm allowed to do that. Notice that 1 over e to the x is the same thing as e to the negative x. That one diverges. And since that is less than or equal to another function at all values, where x is greater than or equal to 3, we know that by the direct comparison test, the integral from 3 to infinity of 1 over x minus e to the x dx must also diverge. Next problem. E to the negative x time or over x, the integral from 2 to infinity. So if I take this, my first thing that I'm going to probably try to do is the direct comparison test. So notice that this is the same thing as the integral from 2 to infinity of 1 over x e to the x dx. That's because e to the negative x is the same thing as 1 over e to the x. So as long as x is greater than or equal to 2, I know that x e to the x is greater than or equal to e to the x, because when you take a positive number and multiply it by something 2 or greater, you're going to get something bigger. So then I can divide both sides by whatever was on the other side. So I know that 1 over x is greater than or equal to, I'm sorry, 1 over e to the x, 1 over e to the x is greater than or equal to 1 over x times e to the x. We proved already that this converges. So because that's true, by the direct comparison test, the integral from 2 to infinity of 1 over x e to the x dx also converges. A couple more problems. Number 7, we have 1 over x squared plus 2x, the integral from 3 to infinity. So in that case, oh, I'm sorry, there's a minus on your paper. Minus on your paper. So the integral here, if we try the direct comparison test, x squared minus 2x is less than or equal to x squared as long as x is greater than or equal to 3. So then we have 1 over x squared is less than or equal to 1 over x squared minus 2x. This guy right here converges by the p-test. However, if it converges and it's smaller than something else, that actually doesn't tell us anything. So the direct comparison test is inconclusive in this case. So because it's inconclusive, what that means is we will try the limit comparison test. And so let's take x squared minus 2x and make that our f of x, or I'm sorry, 1 over that. Let's make that our f of x. And then let's make our g of x equal to x squared. So x squared, 1 over x squared. It doesn't really matter which one we put on the top or bottom. Oh, and I'm sorry, g of x should be 1 over x squared. So we have 1 over x squared divided by 1 over x squared minus 2x, and we're going to take the limit as x approaches infinity. So as we do this, remember by the laws of fractions, we can rewrite this as the limit as x approaches infinity of x squared over x squared minus 2x. Since this would be infinity over infinity, we're going to do some L'Hopital's rule. So the limit as x approaches infinity of 2x over 2x minus 2, that is equal to the limit as x approaches infinity of 2 over 2, since this is once again L'Hopital's rule situation, which is 1. Since 1 is not equal to 0 and not equal to infinity, that means that 1 is an actual number that's not 0 or infinity, and therefore we can say by the limit comparison test, since the integral from 3 to infinity of 1 over x squared dx converges by the p-test, then we can say that the integral from 3 to infinity of 1 over x squared minus 2x dx also converges. Okay, so we just got our first taste of the limit comparison test actually working out. Finally, let's take a look at number 8 over here. With number 8, I would say that your best bet is probably the direct comparison test, but we'll try the limit comparison test first because we haven't had very many times where we've used the limit comparison test. So I would probably try cosine squared x minus 1 over x cubed as your f of x, and g of x, I would try 1 over x cubed, which you know converges. So let's do the limit as x approaches infinity of cosine squared x minus 1 over x cubed over 1 over x cubed. That one, just by the laws of fractions, I can say cosine squared of x minus 1 over 1. So I don't even really have to do anything with that. So that's the limit. I need to just rewrite this because that's chaos over there. So that's the limit as x approaches infinity of cosine squared x minus 1. The limit as cosine squared x minus 1 goes to infinity. That is an inconclusive test, unfortunately. And the reason why it's inconclusive is that we know that it's bounded. We know that cosine squared of x is bounded between 0 and 1, but it doesn't actually give us a legitimate value, so we can't use this test. So let's use the direct comparison test. The direct comparison test, so if we subtract 1 from everything, cosine squared of x minus 1 looks like this, and then we divide by x cubed, that ends up looking like this. And so, since we know that this function must converge, because if we have the integral from 2 to infinity of 1 over x cubed dx, and that converges. If we put a negative on the outside, that converges. By the direct comparison test, we know that the integral from 2 to infinity of cosine squared x minus 1 over x cubed dx also converges. Couple of really quick limit comparison test examples as we close. If we take the integral from 3 to infinity of x squared over x cubed plus 4, what I can kind of think about is, because the powers, if I divided them and I thought about it, I can think about 1 over x as being a good comparison. So if I did the limit comparison with this, when I use the rules of fractions, I get x cubed over x cubed plus 4, and I do some L'Hopital's rule, limit as x approaches infinity, I get 3x squared over 3x squared. That ends up being 1. And so because of that, since I have a limit that's somewhere between 0 and infinity, and 1 over x diverges by the limit comparison test, I can say that the integral from 3 to infinity of x squared over x cubed plus 4 dx also diverges. So that's one thing. Another one, problem 4 on the front, we could take an approach where I use the limit comparison test. I know I use the direct comparison test on the front, but if I make g of x equal to 1 over x to the 5 halves, I do a little bit of algebra, and I end up with this situation. Now, if I did L'Hopital's rule, I'm not ever really going to be able to cancel anything out. But if I pretend like this is equal to y and I square it, then I end up with a limit that's equal to 1 using L'Hopital's rule. So then the limit of the actual function is also equal to 1, because when I square root both sides, I end up with 1, since this is some limit L by the limit comparison test. Since 1 over x to the 5 halves integral from 6 to infinity converges, then the integral of root x minus 1 over x cubed dx also converges. It's a definite integral, so 6 to infinity. So there's a couple examples of limit comparison test.